Okay. Okay, so I'm going to talk about the element of dynamics in future networks and how to manage them. It's loosely motivated by the 5G and IoT networks, but it's more abstractly also a problem of interest. So let me try to give the high-level motivation. So these IoT applications we are envisioning, as well as these capabilities of 5G networks, brings increasing element of distributedness, mobility, large bandwidths, delay sensitivities, and large-scale nature of the networks. So this motivates us to look into decentralized and age-aware mechanisms for controlling the dynamics of various dynamics in these kinds of networks. Okay, so I'm going to try to expand on a set of work that looks at different types of dynamics we have looked into. So the high-level overview or the goal here is to bring together this urgency aspect or age aspect of information that is likely distributed, and the cost of communication for those channels that has to be utilized in conveying that information in the context of distributed setups, and these dynamics that I categorize into three branches. One of them has to do with content, dynamic content. The other is the source states being dynamic, and the other is the users or the demand side of it being dynamic. So on the first front of the caching or the content case, the question is, if the content is being refreshed at let's say the back-end database or closer to the source, how do we keep them fresh at the edge, given that there's a communication cost and of course cache limitations? So the second type of dynamics is where you may have distributed sources. These may be sensors, each having its internal state, and that state is evolving. And the goal here is to transmit the state or track the states at some central node over a common communication channel, like as enabled by these next generation technologies. And the third dimension is about users being dynamic. So you have users with small packets that arrive in the system, need to update it. Like these could be IoT devices that needs to send their updates and leave, basically become passive. So in such a system, over this multi-channel environment that communication can happen, how do we create a low overhead and efficient way of communication? So what we have done is there's a bunch of work. Only part of it is listed here. I'm not going to go through these, all of these, but these try and address these different dimensions and how these dynamics can be managed. So I'll try to overview some pieces of these works in the rest of this talk. So the first dimension is again the content being dynamic, right? So just to again give you the picture here, we've got these source side backend database. There are n items, let's say, and they are being refreshed. So the items content is being refreshed over time with different rates possibly. And there's a fetching cost of sending that content to an edge cache in its simplest form. And that edge cache is receiving demands from users and users according to some general popularity distribution. So therefore, the edge cache can be holding items that are aged if they're not refreshed immediately. So there's a cost to that age. Okay, we call that age of version. And that cost grows with age, but then there's a fetching cost of updating them too. So there's this trade-off. And how do we manage this? So in this, basic context, we've looked at a variety of branches of cases. We've looked at single edge cache and distributed edge caches. And in each case, we looked at various types of caching strategies, some admission-based, some eviction-based. pull, push based, and so on. So we contrasted them, studied them, proved optimality of them. And these differ in terms of what you can assume about who makes the update and who controls this setting. So I'll only discuss a few results from these investigations. So this is the slightly extended setup from the previous case. We still have sources being refreshed with some rates. And then we have multiple edge caches possibly, each one having its own, set of users it's serving. And these, requests come at some rate beta. And they have their local caches. The question is, how do you maintain the content of these caches, keep it fresh? And you may also have the capability of multicasting content to these multiple caches at once, which is an added feature of a wireless environment. So in that framework, we looked at two cases, one single edge caching. So in this case, you don't have multiple caches, but just one cache. And we found pretty precisely the effect of popularity, these costs that I've told about, the rates of requests and such, and the refresh rates, the lambda n. So this is the new component. So this shows how the refresh rate, the dynamics at the source, is integrated into how you value content. So what you would do is, after you find these values of different contents, you order them, and then based on the ranking, you can cache the ones for which you have cache space. Okay, so this is really showing us the effect of the freshness, which was new. It wasn't existing before. In the distributed caching case, we looked at another problem. In this case, the control is not only whether to cache an item, but also how many replicas of the item to keep. If the item is highly popular or has favorable refresh rates, you may keep multiple copies of it. So this, again, we found the correct metric for it, which characterizes how many we should cache and how many replicas we should have. We also looked at, in a related work, the setup where these demands that we had at the edge, the end users, are also flexible. So there's the potential of load splitting. So they're not fixed populations, but we can steer demand into the caches we like. So we studied the optimal load splitting in this regard. We have formulated, the details are in papers. I'm not going to get into the detail of that, but we have explicitly characterized how to split the demand between the caches, how to distribute the items across these caches so that we have multiple copies potentially, and find the optimal way of operating such a system. There are some interesting insights from this investigation. For example, even if the everything else is symmetric, it turns out that splitting the incoming demand equally is not optimal necessarily. You may need to steer more of the content to a cache, and it might be even a cache with a smaller size. So these kinds of things occur, and also this multiple copies phenomenon appears in non-trivial ways. So various interesting insights came out of this, besides the prescription of how to incorporate these refresh rates. So that's the first dimension. In the second dimension, we have looked at this case, as I mentioned, of tracking sources whose states are evolving. We took them to be evolving randomly in time. So as these evolutions are happening, these distributed sources, the transmitters that they have need to decide on making updates to the receiver, where the receiver is trying to keep a good estimate in terms of the squared error measure. But this communication has to be done over a shared medium, and therefore there's a cost to how much you have to pay for sending updates, and that's a function of how many updates are happening simultaneously. So that function, we took it to be a general form function. There are two cases of interest. One is where that function is a superlinear function. So this is a scenario like a random access setting where updates are done independently of each other, and there needs to be collision resolution or some sort of control. And the more updates there are at the same time, the more you have to pay, more than a linear amount. So this would be the superlinear case. In the sublinear case, this different setup where you might have one transmitter collecting information from multiple sensors, and transmissions are less costly if you have more of them because of the common overhead that they pay. So in that setting, we would have a sublinear cost. What we did is to look at both of these cases to try and understand what to do in each case and what gains can be received from it. In the case of a superlinear cost, which is kind of provided there on top, we've looked at two scenarios. These two came up as the strong ways of operating. One is more distributed, which has the threshold-based update rule. In this case, each sensor or each source looks at the error at the time. And if the error exceeds a certain amount, it makes an update and then refresh the error to 0. In the case of the centralized, it's a different procedure. In this case, the transmissions are organized into roughly periodic schedules. So in order to keep the transmissions somewhat flat over time. So these two paradigms, we've studied their performances, and we have observed theoretically as well as numerically that distributed updates is a good strategy up to a certain level. And beyond a certain number of sources, it starts to become worse than the centralized one. So we characterize that threshold point, that transition point, and it also revealed these insights that came along with the analysis. In the case of the sublinear cost, in this case, we've come up with a new policy. So this new policy is called the max K policy. What it does is it updates the K most erroneous sensors. So if K is 1, that would be each user, once there is an error in one of the estimates, you make an update. If K is all the number of sensors, then you would wait for everybody to be sufficiently erroneous, which might be too much to wait. So both of these extremes turn out to be not good. The K needs to be somewhere in between. And that optimal point we've characterized, we've studied, and with the choice of an optimal K, the gains we've also studied, and it shows increasing gains compared to both of these extremes. So let me move on to the third dimension now. This is to do with spectrum access. So in this case, we've got a frame-based setup of multiple bands, frequency bands, there are M of them, and multiple time slots. So these K and M, the product of the two, in fact, describes the capacity, or what we call the C, virtual capacity of the channel, basically. So at the beginning, the way the system works is the following. You've got a certain number of users in the system, N of T here. These can be active IoT devices, as I initially said. What's done in the beginning of the frame is to send a public feedback we have to design that's received by all these users in the system. And they will activate based on it. They'll make a decision to activate independently of each other. And then based on how many are active, you get certain X number of them active, which is a random variable. And once that number of activations happen, there needs to be a question of whether they're successful. And that success model is captured by this shape, threshold-based structure, which basically says that if the number of active users is less than a certain threshold, they can succeed. If it's beyond that, they basically fail. This kind of structure is actually closely approximable with methods, more enhanced MAC methods, which came up more recently, such as successive interference cancellation. So we've taken this as a good approximation for our analysis, but then later we considered how to apply it to more practical cases. To continue with the model, so number of active users is determined and there's a potential success. If the success happens, those users that have completed their transmissions leave. And at the end of the frame, we have another set of users that might arrive. So these new set of users, A's, are random. They have a mean of lambda and a variance of sigma square in every time slot, basically. So the question is, well, how do we operate this system? How do we determine the feedback mechanism as well as the activation mechanism to keep the system running efficiently? We've studied two paradigms for this. One is the congestion-based paradigm, the other is age-based paradigm. So in the congestion-based paradigm, the idea is to try and estimate the active number of users in the system, you know, and what I called N, but this needs to be estimated because nobody has full knowledge of this. So the simple feedback in this case is simply the current estimate of N. So that N hat is sent, that's the congestion level. And then each user is either active or inactive with a probability of R star over that N hat. And R star is optimally fine. I mean, it's fine according to a maximization, which is numerically solvable. Now, based on whether there's a success or a failure, N hat is updated. That update rule is characterized. It is intricate, but it's very simple. So we need to find the correct update parameters here, but they are all well described. So that's the one rule. The other is age-based. This one is differentiating the users in terms of their ages, and it simply announces a threshold on that age. So if the age of the user is above the threshold, it activates, otherwise it doesn't. And if there's a success in this, there's an update rule on the threshold. And if it's a failure, there's another update rule. So we've characterized all of this. These are two fundamentally different ways of operating the system. One of them, the first one, congestion-based, leads to the activation that's Poisson distributed in a limiting sense. The other age-based one leads to a Gaussian distribution. The Poisson distribution has a single parameter, so it's less flexible in that regard. The Gaussian one has two parameters, lambda and the sigma square, the variance and the mean. So they're different in that regard too. But we were able to prove that for both of these designs, we can characterize the stability regions that's depicted here in the x-axis of the lambda mean rate and the y-axis of the standard deviation of the arrival process. So the age-based one is the triangular region, saying any arrival process which is inside the triangular region is stabilizable. The other one, congestion-based, has a horizontal, more rectangular shape. There's no upper limit to it, really. It doesn't care about the variance. It just cares about the mean. Neither of the two is strictly better than the other, as you can see. But one thing is, as you increase the size of the system, the frame size and the capacity of the system, they're both asymptotically optimal. Both of them change as we increase C towards the limit, which is the maximum possible. So they're both optimal in a sense. Their age performances differ, and age-based mechanism works better from the congestion-based one because it's prioritizing the higher aged ones. And we later applied it back to a more practical scheme after we got all of these designs. Okay, so I should wrap up. So in conclusion, so I guess what I'm trying to convey here is these IoT applications and the next generation technologies enable us and expand our horizon and call for new methods of caching, measurement, and spectrum access. We've developed some of them here. I mean, as you just basically got an overview of some of them that looks into content dynamics in caching, source state dynamics in remote tracking, and user demands in the spectrum access case. And these designs, in all these cases, show substantial gains. I mean, the incorporation of dynamics makes a big difference. Without it, things can really fail. And there are some new insights that came out of that, besides the mechanisms we have developed. So I think that's the end. Sorry, I exceeded 20 minutes slightly.